Welcome everyone to the EasyPower Tuesday Refresher. This is Jim Chastain, and today we're going to be talking about the use of PowerFlow, the PowerFlow module, to anticipate or prevent problems with PowerFlow correction. So welcome to everyone, and I invite you to join the conversation. So we're going to start with two poll questions, and I appreciate your feedback. Just a little bit of a data point to help direct some of the dialogue. And the first one is EasyPower PowerFlow part of your current EasyPower suite? And hopefully, if it is, this episode will be particularly productive for you because I think it gives some insight into how to bring extra value to your communications with your customer. Looks like it's kind of split down the middle. And then the second question, as you do studies, do you provide the EasyPower DEZ file, the digital file, to your clients as part of the deliverables? And again here, I kind of have a ulterior motive, and I'll kind of get into that during this discussion. Now, the purpose of today's session is not to cover this topic exhaustively, but essentially talk about how to use the tools. At least the example I'm going to go through is on a what-if basis, but the point that I like to make as an underlying message is that if you consider the arc flash compliance, if your customer considers complying with arc flash regulations as an investment and not just an expense, then there could be an expectation of recouping the cost at some point in time, and this is one of the methodologies to extract extra value from that investment that was made, because the same database that's used for arc flash can be utilized for optimizing the system and looking at more day-to-day operations. And the point that I would suggest is that the EasyPower digital file is high value, and I would suggest it should be delivered with each study because it's something that other suppliers can't provide, and there's reasons to kind of take that a step further. If your customer had some way to look at the data and be able to go through some what-if type scenarios as far as adding components or making changes to a system, it would be an effective vehicle to be able to send that modified file back to you to both advise his decision and or update his system as far as its compliance issues. So frequently we'll find that the database itself, if you're on the same platform, the EasyPower platform as your customer, it can become a more efficient way for him to utilize your services without having to stop his operation, bring you in for a formal quote, and make the whole operation more streamlined. So in terms of recouping some of that investment, power factor demand penalties are an easy target, and that's kind of where I'm going with this today. On virtually every website of most large utility companies, you will find a discussion of power factor. And for the layman, primarily, they describe what it is, why it's an area of concern, and somewhere in the fine print, and sometimes in bold letters, there's a discussion of how the utility company will encourage you to reduce your power factor demand, and usually that takes the form of some surcharge or some penalty above the cost of the real power that your company consumes or the client's company consume. And so this varies in region or state and from utility company, and it applies it applies to all of us, but the largest demand and the power factor penalty itself applies primarily to the large industrial electrical users. But the topic of the inefficiency due to power factor is an issue that affects everyone. It makes our use of electrical power more inefficient, but in specifically with relation to large industrial users, it ends up being an area where a large, potentially very large, penalty can be assessed. And as I say, these are explained on the utility websites. In this case, here's a Con Edison website that explains what power factor is and the fact that they're going to encourage businesses to be more mindful by assessing a power factor penalty when efficiency or the power factor is less than 95%. Now, as I say, this effect will affect anybody as far as the efficiency of our use of electrical power, but the power factor penalties apply most specifically to large facilities. So this excerpt from the PGE website talks about greater than 400 kW users, and then they go through a calculation of what that penalty will run. And as you can see on this next, when we get into the example, this can be significantly large. In fact, on the PGE website, there is a discussion about a customer with a typical 400 kilowatt usage being able to recognize $1,500 per month just by correcting a power factor back to a nominal value. This applies to folks not just in the U.S. Here's a website from a Malaysian utility company, and they're pretty bold about the fact that there's going to be power factor surcharges if people don't stay in line. So that's the reason for this discussion. Now, and again, some companies may not even know it's applying to them, or they see the line item on their utility bill and not know how to do anything about it. So just real briefly, the power factor, the power delivered to us by a utility company is a combination of two things. Basically, the real power, which does the work, and that's what we purchase to be able to do work with the electrical energy. And then there's reactive power, which is an overhead that this utility company has to supply just to get the energy to our plant. Well, these two elements combined are called apparent power, and that's the total that the utility is required to provide just to sell us the real power. And so the higher this reactive power element is, the more inefficient the delivery becomes, and there's at that point a burden on the utility company to improve the connections, improve the transformers, the size of the transformers, and that's why they're motivated to encourage the end customer to be more efficient. Now, another way to look at this, an analogy that you'll find some people describe on the website, is a horse carriage analogy. If we have a railroad car mounted on rails and we want to move it down the railroad track, but because of the ties being an uneven surface, a horse can't pull us in line with the rails. The horse has to pull on a parallel roadway. So the connection to the horse to the rail car will be at this angle. So as the horse moves forward, he's moving the rail car, but he's having to apply a force that's not in line with the direction of movement. And so this horizontal force, or in this case a vertical force, is representative of the reactive power, which is inefficient. The real power is the one that's in line with the direction of the rail car. And then what the horse has to supply, or in this analogy what the utility has to supply, is this apparent power at an angle. So consequently, it takes a bigger horse to move this railroad car than if we had the ability to put to reduce this angle, and in effect we would be able to use a smaller horse to do the job if we were able to just pull straight on a flatter surface. So as cute as that analogy is, the correlation ends right at that point. But the bottom line is power factor is defined as this ratio of real power to apparent power. Now in the U.S. industrial base, over 60% of the industrial load is inductive. And when we pass AC current through any inductor, it causes a phase shift between the voltage and the current. And it's this phase angle that's proportional to the power factor. So the cause of the problem, or the thing that's generating this power factor issue, is the fact that we have so many motors and industrial loads in our population using the utilities. So one way to compensate for this power factor, or this induction, is to provide capacitors in the system to offset the inductance. So that's just one approach. There are others, and we will talk about those later. All right, so on a what-if basis, we have a customer that's designing a large industrial system. He's going to have half a dozen or so large motors, and there's going to be long cable runs to each of these loads. And so the concern is, what do we need to do, or how big of a problem are we going to have with power factor when we deal with this? So let's jump into the tools and talk about that. So again, we've drawn basically on a sketched basis, and if we were to go in and look at this, we see that we don't have many, if any, of the protective devices that you normally find in a circuit like this, and we're starting off with an infinite utility source, again on a what-if basis. What I want to look at is my loading. Down here we got half a dozen or 8 600 horsepower motor, and as we look at these and database edit, we can see that we've set these up, calculated the short circuit. At some point we're going to plot the thermal limit curve, and in PowerFlow we're going to say, well, most of the time these will be running at about 40%. So that's, and we're not worried about starting right now, although at some point in time we will be, and so we may go back and work with the electroder multipliers. But for right now, my primary concern is what the effect of having all these loads on the line will do to our power factor. So I'm going to enter PowerFlow, solve the equations, and by solving the equations we get the voltage and the currents. In fact, it's worth kind of talking real briefly about the readouts that are available. So if I kind of undo some of these check boxes. First of all, it shows us the voltages at every bus. So if we're anticipating a long cable run, one of our concerns is going to be how much the voltage will drop. And if this starts out at a 4160 bus, we can see that we're getting a fairly significant drop on some of these secondary loads, and that might be a concern as we start to get further into this discussion. We're going to talk about generator data in a second. We don't have any generators, so this icon shows us the motor and load data, which we're going to want to be able to see. So what we see here on this motor is that during normal operations at quiescent point, stability or stabilized, we see a 65 kilowatt real load and a 45.6 kVAR apparent load or reactive load at each one of these that's running at 45%. And we get over here to these others. I think we're running these at 50%, and so consequently we see a little bit higher both real power and reactive power. Now, the part there's two parts, I guess, that we want to consider. First are the losses that we see. So we're going to show the losses in each one of the cables. You can see here we're seeing a loss of both real power and reactive power at each one of these cable runs, and some are fairly significant. And the higher the reactive load, the higher that apparent power loss is going to be, because there's higher apparent current flow. Now, what's telling is our ability to display different elements or different SKUs, if you will, of this particular data. So if I right-click in an open area and look at PowerFlow options, I can control what's being displayed in my one-line output. So my branch flows right now, I'm looking at current. If I want to look at current in amps, and then we look at our branch flows, we'll see that we have 30 amps in this case, in this particular leg. And if we look at it in real power and reactive power, we see something obscured by my label here. We see 555 kilowatts and 335 kilovars, which is producing this loss that we're seeing on the side. So I'm going to get rid of the losses and focus on the kilovar draw. So we take this all the way down to the motor load. And each one of these legs feeding these dual motors, we see we have 131 kilowatts and 89 kilovars, 90 kilovars. So at least on this side, I'm seeing something like a 90 kilovar load or a 90 kilovar apparent current flow, reactive current flow. And here it looks like it's 112 for each of these dual loads. Now, one of the things you want to double check, and this is how you tune the model, and that is specifically what the loads are running at. So these can be, as we're in PowerFlow, these can be adjusted by scaling our load factor, scaling our loading. So we can scale all the loads, the constant loads, the motors, or MCC and panels, and see what's going to happen as we make that adjustment. For instance, as we reset these two motors to 100%, you can see that if we were carrying a heavier load on this side, it would draw a much heavier inductive current through this leg. But for right now, we're going to stay with our initial 40% because we've already made that the load flow setting. All right, so at this point it looks like we need to offset about 90 kVAR on each one of these legs on this side and about 112 kVAR on each leg on this side. So let's, before we jump into doing the what if adjustments, I want to come up and look at what's being generated on my load. So I want to look at my MVA and power factor. And I need to look at the branch flows. And so we see coming out of the utility 1.2 MVA and a 0.837 power factor, which according to the website, if we were on a PGE hookup, could be costing us somewhere near $8,000 to $10,000 a month with this much demand on with this kind of a power factor load. So the question is, what do we have to do to make adjustments to be able to bring this power factor back in line? So let's go back to our database edit. Already got a scenario set up where I've added some capacitors. So now the capacitors just need to offset the that reactive current we were seeing with the loads we were talking about. So let's go back and see how that looks. And again, we're just doing this on a what-if basis. So the question is, what if we wanted to offset some of this power factor demand with these inline capacitors? And so where we had a 98 kVAR reactive inductive reactive power we have to compensate, we're going to put in a 95 kVAR capacitor in each one of these. And on the right-hand side, it seems like I went with a little bit higher. Oh, I went 95 kVAR across the board. Okay, let's go back to power factor. Solve the equations. All right, so now we can see we have our 99 kVAR capacitive draw, and we reduced our inline. Let's go back and take these back to kVAR. We've reduced our inline draw upstream to just under 10 kVAR versus the 100 that we were seeing before we had the capacitors in there. So clearly this has reduced the load, and where this is making us more efficient is now all that current doesn't have to pass through all these long cables as it goes back up to the utility. And the bottom line is, by putting those capacitors in, and frankly it's not necessary to get it all the way to 1.0, but above 95% was what we were shooting for. So we accomplished our goal. The next question is, what does it cost to put those capacitors in? What's the most efficient way to get there on a what-if scenario? So the question that's interesting in my mind is, where does that current go? Where does that energy go if it's not going up to the utility? We still have the same reactive current going through the capacitor, going through the motors, but now instead of going up through the utility line, it's going back through our capacitor. If I open up this switch, you can see it takes our capacitive draw back to the utility, back to the 90 kVAR, but we haven't changed the draw by the motors. So quite literally, we're keeping that energy in-house, and it's circulating back and forth through the capacitors rather than being a burden both in efficiency to our system, but as a power factor demand on the utility. The other interesting thing, and the other reason for having a capacitor in line, and another reason we might want to maybe bring these values down a little bit, is that we've also, now that we've eliminated this loss that's going to be in the cable and the transformers, we've actually brought the voltage up, and so our motors are going to be more efficient just in their normal operation. The bottom line, now I don't mean to oversimplify this discussion in terms of the actual design of a power factor correction circuit. All I wanted to do is come up with some first order approximation on what type of power factor correction I would need, and then work backward from there into how to make my system more efficient, and then equate that to what the cost of designing the power factor correction will be. The bottom line is the return will be ongoing, and so can be amortized over the life of the capacitor banks. The other element, and we'll cover this next week, the other element that steps into this conversation now is harmonics. And if it's something that's easier to deal with when we're talking about a new design, but if this was an existing facility, a very important next step then is, once we've ascertained what level of capacitance we need to improve our power factor correction, what does that do to the resonance potential within our system? And that's one of the benefits of the EasyPower harmonics module. So let's kind of step back into the PowerPoint. Hopefully that was illuminating for some folks. And I just want to say that a conversation like this would be extremely valuable to a client. It's something that he could easily see if I supplied him the one-line diagram, and we could communicate much more efficiently, and he could, again, see for himself that the benefit was real, and consequently, I believe it builds up a trust and a more productive synergy between you and your clients. So that's the moral of the story. Appreciate everybody for attending today. By all means, utilize the website easypower.com for other information on the tools, other webinars. Okay, appreciate everyone from attending. By all means, if you got other questions, you can contact us via email or contact tech support easypower.com, and look forward to you all joining us next week when we get into the harmonic side of this equation. Have a good one.